Welcome to the first ever Corundum developer meeting. It's great that all of you guys were able to find the time to get connected. So for all of you that aren't aware, my name is Alex Ferencic. Over the past number of years, I've been working on this little project called Corundum. You might have heard of it. So today we're going to talk about the future of the project. All right, so let's see. So this meeting, I've got a couple of goals that I'm hoping to accomplish. The first one is that I think there's a lot of great stuff that could be done around Corundum if we have, a decent community. So what I want to do is, kind of facilitate communication, get people in the same room, and perhaps get some channels of communication open so we can do some more interesting stuff with Corundum. The second goal is to kind of set some expectations. So I got some ideas about the future that I want to take Corundum in. So I want to convey those, and I also have some development logistics that I'm just going to go over very briefly, just so people are on the same page. And the third goal I have is to identify perhaps some potential contributors, because I've been working on Corundum for about 3 years or so, and basically all by myself. So I've accomplished quite a bit, but there's a lot more that we could do if we had, some additional hands and some additional support. All right, so if we can just keep these meeting goals in mind through the rest of the little presentation that I have here, that would be great. All right, so now for the agenda, I got some slides here that I'm going to go over that talk a little bit about the kind of current status of Corundum and a little bit about the development history, so you have a little bit of context. And then I'm going to talk about the future of Corundum, right? So what I'm thinking about doing going forward. And additionally, I'm going to talk a little bit about logistics, just a couple of slides, so no worries there. And then after that, I'm going to open it up to technical discussion. So I think there's some folks on here that are interested in Corundum. So hopefully we can have a bit of a discussion. Yeah. All right. One other thing before I get too far into the presentation is if I can ask everybody to do a couple of favors for me really quick. First, if everybody can go down into the Zoom chat and just put in your affiliation and hit send. You can send it to me or you can send it to everyone. That's fine. Just the company you're representing or the university or that you're affiliated with, or you could just say hobbyist or FPGA enthusiast or something like that. I just like a record of who's interested, basically interested enough to connect to this little Zoom chat. And then second, I have a link here on the slide, join.corundum.io. If I can get everybody to pull that up in your web browser, there's 2 links on there. The first one is a link to the Corundum mailing list. So if you're not already on the Corundum mailing list, but you're interested enough in Corundum to join the Zoom meeting, you should probably be on the mailing list. So if you could add yourself, that would be great. Second is there's a little survey. You can fill it out now or you can fill it out later. I'm basically just asking, what is your interest in Corundum, and would you be interested potentially in contributing something? I figure the activation barrier is a little bit lower, asking people to check some boxes than to send me an email. So if that's something you might be interested in, then fill out the survey and I'll follow up later on with an email. All right, so that rounds it out for the agenda. So I'm going to go ahead and get into the slides that I have for today. These will probably take half hour to 40 minutes or something like that. I'm going to try to keep it on the short side so we have time for discussion and whatnot. All right, so part 1, the genesis of Corundum. So I'm currently a postdoctoral researcher at UC San Diego, and the research group that I'm affiliated with focuses on data center networking. I've actually been a part of this particular group for a number of years now. So I'm going to talk kind of a little bit about what the research group does, because Corundum was heavily inspired by some of the work that we've been doing at UCSD. All right, so one of the main things that we look at in our research group is something called circuit switching. Circuit switching in data center networking applications. Now, so traditionally, data center networks are built with devices called packet switches, and packet switches are great. They make independent routing decisions packet by packet, and you can use them to build very large networks. they form the internet basically, and they're great for use inside of data centers when you want to build, high bandwidth networks to interconnect a whole bunch of nodes. But there's a problem. Network packet switch bandwidth and link bandwidth are not increasing fast enough to keep up with, demands for bandwidth inside of data centers. So as a result, the data center network, building those for modern data centers requires a huge amount of capital, and the network, once it's built, requires a huge amount of energy to run. So one possible solution for this that we're looking at UCSD is optical circuit switching. So the idea is that instead of routing individual packets, you make and break connections in the network in the optical domain. And this has some pretty significant potential for power and cost savings. We're talking about, an equivalent optical switch having, a power consumption of hundreds of watts versus an electrical switch having, kilowatts or tens of kilowatts of power consumption for a similar number of ports and bandwidth and whatnot. But there's always a trade-off. Optical switches require a totally different network design because they operate on a totally different switching paradigm, right? They're operating on a level of links instead of a level of packets. So this means you kind of have to re-architect the whole network around the switch. At UCSD, we don't just think about this stuff from a theoretical standpoint. We actually build research networks with experimental switches and commercial servers to try to get a feel for how all the pieces need to fit together. And so we can experiment with different optical switching technologies. We can get an idea of what characteristics the switch need to have, how it affects the operation of the application, and so on and so forth. One of the most important components that we need for this to work, or one of the most important functionalities, is the ability to very precisely control when packets are sent into the network in time. Because in a sense, in a circuit switch network, the routing for a specific packet is determined by when that packet is sent, right? Because it has to transit the switches when they are in the appropriate configuration. If it's sent too early or too late, then the packet will end up at the wrong destination. So what we need to be able to do to build an effective circuit switch network is send these packets on kind of the same time scale as the switch reconfiguration. And we also need to be able to do that kind of on a per destination or per flow granularity. We've tried a whole bunch of different solutions over the years. If the switch is slow, like millisecond time scale, you can do everything in software and it's fine. But if you are microsecond time scale or faster, then software is not good enough. You have to do it in hardware. Unfortunately, there's very limited hardware support for controlling the flow of packets on commercial NICs. Maybe you have just a handful of queues, which isn't enough for per destination operation. And maybe you have some rate limiters, but that's about it. Commercial smart NICs have architectural limitations. Sounds really good because they're programmable, but they're geared towards making routing decisions or making minor packet modifications, and that's about it. So that really means that if we want to do this, we need some sort of custom hardware, right? Because we're a research group, we're not going to be spinning a NIC ASIC, so that basically leaves us with FPGAs. So the question becomes, how do we do this on an FPGA, right? We've used FPGAs in the past for sending packets at precise times, for controlling the optical switches or for basic time synchronization purposes. But this is all using packets that have been generated inside of the FPGA. So can we extend that to controlling packets coming from, a host system? Ideally, what we want to be able to do is have almost a standard commercial NIC and then drop a, new scheduler on there that's aware of, some synchronized notion of time. We could use that to control the flow of traffic. But when I started working on Corundum, there was, no such design available. Nothing, at least, that we could, pick up and modify and use for our purposes. So that really left the only option remaining is to build a custom NIC from scratch. Now, how hard could that be, right? Spoiler alert, it took a while. So I started working on this in around 2018 or so. And I spent a long time looking at, the Mellanox device driver source code and Linux kernel source tree and whatnot, and started from the PCI Express interface and started working my way across to the Ethernet interface. And as things started coming together, it became clear that, even setting aside all the circuit switching that we wanted to do, just the NIC aspect alone is going to have implications, beyond what our research group can do, right? Because if you have an open source NIC, you can build all sorts of new and interesting functionality on top of that. So what we decided to do is, instead of keeping this internally and just using it for our own purposes, we would just make it open source so everybody could take advantage of it. And then obviously, we would build it with the architectural requirements that we had for circuit switching, and then we could use it for our experiments as well. So started development in 2018. We announced it at the OPSIS workshop in SIGCOMM in 2019, and then published it at FCCM in 2020. And well, here we are now. So I think we've accomplished something useful. So anyway, for those of you who are not already aware, I'm going to spend just a couple of minutes talking about kind of some of the high-level details of Corundum. So it's a reference open source FPGA-based NIC. It's extensible, so it supports adding additional custom features if you want. It could be simple application logic, or maybe you need to dive down deeper into the data path. The key application for this is the hardware prototyping of experimental networks and protocols, which is exactly what we're doing at UCSD. We're building new networks and we're running experimental protocols over them. All right, so very brief overview of the high-level features of Corundum. This slide has been another presentation, so I'm not going to spend too much time talking about it. But Corundum supports basically whatever PCI Express interface the target board supports. So that could be PCIe Gen 3x16. It supports high-performance Ethernet connectors as well, 10G, 25G, 100G. Again, whatever is on the board. It has a high-performance DMA engine. Now, the DMA engine is really the core of the NIC, so it has to be properly integrated and everything. And that's the case in Corundum. And we have a device driver to connect everything to the Linux kernel networking stack, so you can use this thing as a normal NIC from the standpoint of the operating system and the applications. And Corundum can control data on a per destination basis through supplying tens of thousands of transmit queues. And we have customizable schedulers that you can use for controlling the flow of data. If you take that and you couple it with time synchronization, then you can perform microsecond precision TDMA at a data center scale. And the design is relatively high performance. It can hit around 60 gigabits per second with the 1.5K MTU frames, and it can get much closer to 100 gig line rate with 9K MTU frames. And all the source code is up on GitHub. I'm sure a good number of you have already looked at that, but if you haven't, you're free to take a look at that. All right, so this is a block diagram of all the components that are in the current NIC. I'm not going to talk about this too much, but I'm just going to go over this at a very high level, right? So we have at the top level, we have the interfacing logic that sits on the FPGA, right? We have the PCI Express interface, we have the DMA interface, and we have a PTP clock. And then we also have on the other side the MAC and PHY interface components. And then inside of that, we have one or more interface module instances. These modules are exposed to the operating system as individual network adapters. And all of the queuing is associated with the interface. So the transmit, receive, completion, and event queues are all located in the interface. And then inside of the interface, we also have one or more port modules. And the port modules contain the actual transmit and receive data paths, along with the transmit scheduler and the checksum offload and hash offload components. So that about rounds out the kind of high-level design of Corundum. It's relatively straightforward NIC design. And if you wanted to add, some on FPGA logic, then you can cut the connection between the MAC and PHY and the rest of the design and insert custom logic if you want to. You can also connect to the DMA infrastructure. But one thing we don't have is like a nice little box that you can put your application logic in that some other platforms have. But this basically brings us to the state of Corundum today. It's basically how it looks. Over the past year, we've made some modifications, but no major architectural changes. So what do we do with Corundum going forward? Well, so this discussion was basically kicked off by Tao Wang, who asked on the mailing list, how do we implement RDMA in Corundum? I'm like, well, that's not exactly a trivial thing to do. But if you guys are interested in actually helping make that happen, that's not an opportunity that I want to pass up. So I sat down, I did some ruminating, if I'm going to take RDMA and Corundum and put them together, what could we do with that? What would that look like from an architectural perspective? And well, this is what I came up with. So the idea is to take Corundum, and turn it into a platform for in-network computing. Now, if you're not aware, in-network computing is a somewhat hot topic in the data center space right now, where you can take some application functionality that would normally run on the CPU and you can push it into the network somewhere. So either you can run it on the NIC, usually a smart NIC or something like that, or you could potentially even push it into like a programmable switch. So part of what I want to do is to add an application section where you can, nicely insert some of this, custom logic onto the FPGA. The other thing is to implement RDMA. Now, RDMA, if you're not aware, is RDMA came kind of from the InfiniBand high performance computing world, and the idea with RDMA is it's a protocol that's implemented mostly in hardware, and it's basically kind of a kernel bypass framework where the applications can directly interface with hardware on the NIC, which implements most of the RDMA protocol stack. And what this allows you to do is perform relatively low overhead data transfers between hosts in the network. All right, so what I want to do in Corundum is implement an application section and implement RDMA as basically a first-class feature by modifying the data path in Corundum. And then in the application section, we'll add hooks and interfaces that allow application logic to access, other features of the NIC, as well as accessing host memory and things like that. And the idea is to open new opportunities for partitioning compute between the host and the FPGA. So this is a block diagram, again, of the current design of Corundum. And this is a block diagram for what I am proposing we do with Corundum. So there's a number of important changes to consider here. The first one is that we're going to bring up, any on-card memory, be it DDR, on-card DDR4 or on-package HBM. And then that's going to be connected via the PCI Express interface to the host, so the host can interface with that through one of the PCI Express bars. And then we're going to add an additional DMA interface module so that components on the NIC can access both the DRAM and on the card and the host memory. And it should be possible to basically read out the bar setting and then use that to determine which DMA engine to use. And if we do that right, then that will result in a unified address space. So both the host, software running on the host and other PCI Express devices as well, and logic running on the card will have the exact same view of not only host memory, but also on-card memory. So you can exchange pointers to, buffers anywhere, be it on the host or in the card, without having to do any additional address translation or anything like that. So that's going to be a pretty useful component. Inside the FPGA design, we're going to add an application section that sits basically in the main transmit and receive data path. So the application will have access to all the network traffic. It'll have access to the DMA subsystem. It'll have access to HBM or DDR via the direct AXI connection. It'll have direct feed from the PTP clock if you want to do anything time related. And we'll also modify the core data path to support RDMA. And that about rounds off what's going on in this block diagram. So if we're going to enumerate kind of all the main changes, what we're going to do is add RDMA support to the core data path. We're going to add support for variable length descriptors. Now, descriptors, if you're not aware, are basically how the NIC driver communicates with the hardware. So each descriptor will describe an operation that the NIC is going to perform. So variable length descriptors means that you can handle both simple operations and more complex operations that require, more instructions, if you will, efficiently. Right now, Corundum uses fixed length descriptors. They all have to be the same size, and that's not so great from a performance perspective. The logic to support variable length descriptors requires a bit more work, but it also comes along with, descriptor caching and prefetch and whatnot, which can improve performance. And then we're also going to modify, as I said, the DMA subsystem to kind of merge the on-card memory in with the system address space. So you have a unified DMA address space that looks the same both from the host as from the card. Now, I know this is going to work in terms of physical memory. I'm not quite sure at this point how it's going to work in terms of virtual memory and whatnot in the context of RDMA, but we'll figure that out. And then I'm also going to do is add, the application section. So we have a nice box. You can put your custom application logic in, and that'll have various interfaces to connect to components on the FPGA such that the application logic can take advantage of everything. And then I also need to pull kind of the data path out of the port module and move it into the interface. And that's necessary because RDMA has a lot of shared Q pair state, and all that's going to have to be handled in a centralized location. And the hope is to be able to do all of this while preserving all of the current features of Corundum and all the current device support. So, the trade-off here is we're probably not going to be able to run RDMA on every device. So what we're going to have to do is implement it in such a way where you can, turn it on and off by a Verilog parameter. So if you need RDMA, you turn it on. If you want to use those resources for something else, you can turn it off if you're just going to be doing Ethernet. Let's see. And then the other thing that's going to be useful is, for what we're doing at UCSD, we need to have the transmit schedulers in control of everything. So this isn't a feature I've really touted too much so far, but that also means that for the RDMA stack, the transmit schedulers are going to be in control of every packet that the RDMA stack sends. So if there's anybody who's interested in doing, flow control or congestion control on top of RDMA, well, Corundum will give you a way of actually controlling what the RDMA stack is doing, which could potentially be useful. So I'm going to talk just a little bit more in detail about the changes to support RDMA. And the general goal here is to rebuild the data path to support RDMA as a first-class feature. So we're going to have to revisit the descriptor format to add any necessary fields for RDMA. We're going to have to add logic to parse and build the RDMA headers. And kind of my idea for how that's going to work is, when a packet shows up, we're going to send the entire packet to the DMA subsystem, and then we're going to peel off the headers and process those in parallel. And then the RDMA stack can determine whether the packet is actually an RDMA packet or an Ethernet packet. If it's an Ethernet packet, then we can handle the whole thing. If it's an RDMA packet, then we can use the DMA engine to extract just the payload and write that out into either host memory or on-card memory. So in this sense, we're basically going to be able to use the DMA subsystem to do all the packet segmentation and reassembly without requiring a bunch of additional logic to handle that, which is going to be super convenient, and it should be really high performance. And then we also need to improve the checksum offload implementation, because right now it's rather tightly tied to the Linux kernel networking stack. And if we're going to be generating UDP packets on the FPGA, that doesn't really work. And we'll also be able to use this checksum offload implementation, in the application section if the application wants to generate IP, TCP, UDP packets. So you don't have to compute the checksums yourself. And the goal about the RDMA stack is to have this visible to both host software and application logic on the FPGA, so that you can issue operations from either the host or from application logic on the FPGA. And you'll also be able to terminate RDMA operations against both host memory and on-card DRAM. So, the HBM or the DDR4, whatever's on the card, you'll be able to access that or host memory through this unified DMA infrastructure. And it should be possible for hardware application and host software to use the RDMA stack at the same time, including things like, cross-connecting two Q pairs locally, one on the host and one on the card. So you can use RDMA to interface with the application or with the accelerator running on the FPGA. And it should also be possible to use all this without the PCI Express host interface. So if you want like an embedded context or, for example, a Zinc device where you don't have a server over PCI Express, but you have the ARM cores, then you can use that to control the whole system. And ideally, we'll be able to support the RC, UC, UD, and XRC transports. RD is problematic for a number of reasons in terms of, Q pairs sending to various destinations instead of one destination. And it seems like Mellanox doesn't even implement RD anyway. So if Mellanox doesn't implement it, what's the point? And also, ideally, the software implementation will be standards compliant, so you'll be able to use it with existing RDMA applications. I've definitely seen cases where people will make a totally custom RDMA implementation or a totally custom interface, and I mean, that's fine, but for what we're doing, it makes sense to be able to use things like MPI applications on top of it without having to rewrite everything. So, and the other goal that we have here is to expand the device support. So, I mean, as you guys might already be aware, Corundum supports operation on a whole bunch of different FPGA boards. Right now, though, it's all just Xilinx FPGAs, although we also have boards from Alpha Data, Silicom, and the Net FPGA group. But we have planned support for Intel devices as well, specifically the Stratix 10 MX and Stratix 10 DX, potentially the Urea 10, and also on Zinc UltraScale Plus, but with the SoC as the host. So that's kind of how things are. That's kind of how I'm planning on taking things going forward. All right, so now a quick note on logistics. You're probably thinking, that's a lot of functionality. It's going to be hard to implement all that. Yeah, probably, but I have a plan that I think will make things a little bit simpler. The idea is to basically implement this in several stages, right? So phase one is you implement everything but RDMA, basically. So all of the foundational components that are necessary for everything to work, including the application section and the unified DMA address space and yada, yada, yada. Then phase two, we build RDMA support on top of that. Now we can actually start working on the phase two components before phase one is totally done. So this is a little bit flexible. But for phase two, we implement RDMA that lives completely on the FPGA. So this means that we're going to be using SRAM to store all of the Q pair state and whatnot. And the downside about that is that you're going to be limited in terms of how many Q pairs you can use, but it should be simpler to design the logic and get everything working. And then phase three, the idea is to improve the scalability. Basically, you add kind of a caching layer on top of phase two, so you can implement a much larger number of Q pairs by having a data structure that lives in host memory or on-card DRAM or something like that. And then you can just pull the active Q state into SRAM on the NIC. So that's the thoughts there. And then I have a very basic project organization here that I put together because there's a lot of moving pieces here. We've got stuff going on the software side and on the hardware side. So on the software, we've got the device driver, and we've got the lib verbs, user space components that are necessary to interface with the NIC. And then on the software, or on the hardware side, we've got the DMA subsystem, descriptor management, pipelines, RDMA, packet processing, Q pair states, protection domains, all these various components that are going to have to be implemented. And I could probably put a bunch more boxes on the software side, but to be honest, I'm kind of new to RDMA. I have not read over all of the I've not read over all the specifications on the software side of things, but I do have some contacts that are hopefully going to be able to fill in some of the details. All right, and then so that covers kind of the overall organization. For coordination, we're probably going to be doing most of the communicating over the mailing list. So if you're interested in helping out with any of this, again, get on the mailing list. I'm going to spend just a couple of minutes talking about the code organization and maintainability really quick. So in Corundum, the code kind of falls into a couple main categories. Most of the code is core code that has to run on every target. And then there's also target-specific board that's target-specific code that's specific to each board in each FPGA. And then just a couple of notes on maintainability. In order to make sure that, well, in order to avoid as many bugs as possible, we have a continuous integration framework on GitHub Actions. So this uses CocoaTB and Icarus Verilog right now, but eventually I'm hoping to make it work with CocoaTB and Verilator. So this goes and runs all of the tests in the repository. So this needs to cover all of the core code and then all of kind of integration level tests for each of the targets. And the flip side about using Icarus Verilog is that it doesn't support VHDL, right? So that means all the core code basically has to be written in a subset of system Verilog in order for the CI to work. And then the other thing to keep in mind is that Corundum is a highly parameterized design, right? We use Verilog parameters to change the number of interfaces and the number of ports, the number of queues, and the size of the data path, all sorts of different settings. And there are problems when you bring different languages together for passing these parameters around. So the design is totally in Verilog, it works, but if you want to say incorporate an HLS module into Verilog, you have a problem because you can't pass any parameters from the Verilog design into the HLS design. So this basically means that all the core code is going to have to be written purely in Verilog. It's not going to be possible to incorporate any HLS or VGen or Chisel or Spinal HDL or whatever modules because of this issue. The other thing I'll mention, though, is that all of this talk about RDMA is not really exclusive. I would be more than happy to consider, other features if there's something that you need for your project and you'd be happy and you'd be interested in working on it. I'd be happy to talk with you about it. So SRIOV or XDP or DPDK or, whatever you can think of, we can try to figure out how that would work architecturally in Corundum. And if you'll allow me to get a little bit more concrete for a minute, at UCSD, we're operating under a grant out of the Department of Energy, the ARPA-E Enlighten program. And as part of this research effort, we have a number of different collaborations that are taking place. So one of these collaborations is with Sandia National Labs. And at Sandia, they're going to be putting together a test bed that consists of 16 servers, and it's going to be loaded up with 32 of these very nice Bitware FPGA boards. These are the Bitware 520N MX FPGA boards, and these have the Intel Stratix 10 MX FPGAs with 16 gigabytes of HBM. So for the experiments that we're going to be running, we need the phase 1 features. So regardless of what comes out of this meeting, we're going to be running phase 1 features on these cards at some point in the near future as part of the research project. And then we also have another collaboration with the folks at ISI, and they want to be able to use Corundum for some network emulation, again, as part of the overall research effort out of the Department of Energy. And as part of that, they're interested in XDP support and switch device support. It's a little bit, it's still a little bit rough at this point, but presumably the switch device support will also be coupled with some sort of packet switching support on the hardware side. So we'll see what that looks like, but they're very interested in getting whatever code they put together incorporated into Corundum upstream. So everybody will be able to take advantage of that. And that about rounds out everything that I want to say here in terms of the future of Corundum. So at this point, thanks for listening. Again, I have that mailing list and survey link up here, and at this point, I'll take questions. Let me actually unmute people. Let's see here. Okay, so if anybody has any questions, feel free to pipe up. Hey,
Alex, 2 questions.
Sure.
One is you mentioned in one of the earlier slides that you have separate control per Q pair, correct?
Right.
What is that control doing, and why is it per Q pair? I thought that your purpose was to try to control timing, to match the sending the packet with the connection being set up correctly or right for the time. So shouldn't it be between NIC to NIC pair and not between Q pairs?
Well, I mean, ideally it'd be NIC to NIC pair, but the NIC is really only aware of the Q pairs. So what you can do is, if you want to control, NIC to NIC pairs, you would, enable all of the Q pairs that are associated with the other NIC, in a group, basically. I mean, all of this is kind of up to what the scheduler is doing internally. The scheduler has to keep track of, which Q pairs or which queues have data that they want to send.
So that's what I was thinking. That would be the ideal solution, right? Not the control to Q pair, but per protection domain. Maybe you could use the protection domain as the one controller per protection domain. So all the Q pairs within that protection domain would be.
I mean, you could do that. It's just you have another kind of mapping layer, if you will, that has to be implemented somewhere. So it's unclear kind of how that would work. So with the Q pairs, it's pretty obvious because the scheduler can just say, yeah, send something from Q pair 5, and then Q pair 5 would send it, right? But if it's a protection domain, okay, well then you have to go down into the Q pair, and then something I'm not sure. You basically kind of have to have two levels of scheduling. One to say send from this protection domain, and then you'd have to have some schedule over the queue pairs in that protection domain. So just for simplicity, it makes sense just to have one schedule that just covers the queue pairs directly.
Okay. And the next question is a distinction of the phase 1 and phase 2. When you say the queue pair state is SRAM, when you say the queue pair state, are you talking about which work request is being executed, or the actual work request descriptors are in SRAM?
So when I'm talking about queue pair state, I'm talking about like the current acknowledgement number and things like that. And yeah, just the active state. So all of the ring buffers for all of the queues, all the work queues and the completion queues and everything, that's going to live in DRAM somewhere, probably in host memory.
Okay, so that's what I was confused.
Yeah, actually, with the current setup, or with the setup going forward, due to the unified address space, you could put the descriptor queues either in on-card DRAM or in host memory, and you could even mix it up. Different queue pairs could live in different memories if you wanted to.
But when you mention state, is really counting of packets or something that's are not the descriptors. Descriptors and payload are still with on the host or whatever the queue pair is residing.
Right, yeah.
So queue pair and payload probably will be on the same host or the same memory system.
Right, yeah.
Okay.
Yeah, usually you'd probably do it that way, but you know, you could mix it up if you had to for application specific reasons.
Okay.
All right. Does anybody else have any questions?
Hi, Alex. Ryan Goodfellow from ISI. Can you hear me?
Yeah, I can hear you.
So I just wanted to ask about the feature matrix with hardware support. And so, as you know, we're looking at developing some features for XTP and SwitchDev. And we have some specific hardware that we're working on, but that's almost certainly not representative of the entire hardware substrate that's supported by Corundum. And so do you have like a policy in mind of how contributions upstream are going to be received in terms of like what hardware they may support or not support, or is there going to be like a generic layer that can help us with that, or what do you envision for that?
Well, what I envision is that most cards are going to be running kind of the same core logic, so most contributions I don't expect are going to be dependent at all on the card. The only stuff that's really dependent on the card are, you know, management features. So like how you talk to the transceivers over I2C and how you do firmware updates and things like that. If it's entirely within the design, you know, if it's a feature of the core data path or of the interfaces or whatever, then it should work on all targets.
Okay.
And that makes things actually a lot easier for development because it doesn't really make too much difference, you know, what board you're developing on versus what board you're testing on. So I've been doing a lot of development, you know, on the alpha data board, for example, on, you know, on these guys, the ADM 9v3, ADM PCA 9v3 boards. And then we run on, you know, we just installed a bunch of Silicon boards at UCSD, and that we're going to be putting, you know, these bitware boards in at Sandia. So, you know, you can develop on one and run on a different one if you need to.
Okay, great. Thank you.
Yeah, no problem. Anybody else have any questions?
Well, this is Edmund Hummenberger.
Sure.
So you said, you hear me?
Yeah, I can hear you.
Okay, perfect. So you said you have this partnership with Sandia, and they're putting 16 servers with a bunch of FPGA cards in every server. But you are going to use only one of those FPGA servers for the network side of Corundum, and Sandia will deploy other compute cores on the rest of the FPGAs, or?
Well, so right. So this is part of the circuit switching research that we're doing. So we're going to build a you know, an optical switch that gets sent to Sandia, and I'm not going to go into too many details about that now, but we're building an optical switch. It's going to go to Sandia. It's going to get integrated with the test bed, and then we're going to run Corundum on all of the FPGAs. and presumably run some combination of workloads on the hosts.
So all FPGA boards
it's not a
will
onesie
be
twosie.
put on
We're
the
going to have
switch.
32 FPGAs that we're going to be using. That's going to be hooked up to actually a couple different networks in parallel. So we have some flexibility.
Yeah, now it makes sense. And the second question is, you said you plan for a unified memory space between all the memories on the FPGA card and the host memory to see a unified memory space. And the DMA engine would then be able to work on the unified memory space. But doesn't that generate different classes of memory areas where you have different performance depending on where the actual memory sits?
Yeah. I mean, trivially, it's going to be a lower latency to access, memory that's living on the host versus, or living on the card versus living on the host.
Yeah, but would the application know about that, and would it need to?
Well, that would
account?
be up to the application, developer and whatnot. So if you wanted to, if you wanted low latency access to something, you would want to make sure to copy it into the memory on the NIC.
Okay, so you make it easy on the one hand, but you make it hard for the other on the other hand.
Right. I mean, it gives you the most flexibility. The other thing I'll mention is that you don't have to use the DMA subsystem to access the memory if you want. So this is probably more relevant if you have something like HBM in play, because if you notice the application section, it's connected both to the DMA infrastructure as well as directly to the DRAM. So for something like HBM, the application will actually have access to all of the separate, AXI interfaces. So I think, what was the story with the HBM PHYs? They have something like 16 or 32 separate HBM interfaces to give, just some insane amount of bandwidth, right? Several terabits per second. So the DMA infrastructure is not going to be capable of moving that much data, right? This is mainly, the DMA infrastructure is mainly intended for moving data, to and from the host and over the network. So if you have some compute-heavy application, you'll probably that needs, very high bandwidth access to that memory, you would probably want to point that directly at the AXI interfaces that are facing the HBM on the card. In which case, it won't be able to access any of the host memory at all, but it'll be a very high bandwidth and relatively low latency connection.
Yeah. Do you use IP from Xilinx for the AXI interfacing to the memories, or did you write your own?
I have my own library for that because I can't simulate the Xilinx stuff with the simulation framework that I have.
Yeah, and it sucks.
Well, I'm not going to say anything about whether it sucks or not because I haven't really used it, so not really in a position to judge that.
Yeah, okay.
Yeah, but I mean, in terms of actually talking directly to the memory, we would have to use whatever FPGA interfacing features are supported by, the target device. So for HBM, you would definitely be using, Xilinx's HBM controller or Intel's HBM controller, depending on, what part you're running on.
Thank you.
Yeah, no problem.
Hello, I had a question.
Sure.
Can you hear me now?
Yeah.
Okay. As you know, there are some boards which have 4 or more, not more, but 4 QSFP ports. And if we would add support for that device, should we include constraints for all the GTYs that are mapped to one of those QSFPs? I mean, there would be 16 GTYs, and should we add constraint for all of them? And should we call, or should we instantiate 16 GTYs or something?
Yeah, my usual strategy with that is just to bring up every conceivable interface that somebody might be able to take advantage of. And then, you can kind of remap and connect to the ones you're interested in, at a deeper level of the hierarchy. I don't think there's any real reason to avoid instantiating all of the GTYs. So for example, this bitware board from Intel has 4 QSFPs as well. So for this board, I'm definitely going to be turning on, all 4 of those. So I'm not sure if you have a particular board in mind, but yeah, that would be the idea. Now, whether you make kind of the default design actually use all 4 of them is a different story. Probably what I would do is just turn on like 2 of them, so the design is a little bit smaller. But you can still implement, all 4 ports just to provide the most flexibility.
Thank you.
Anybody else have any questions? So,
sure, I'll hop in with a question. Sure. I'm Giray. For the application area, were you thinking of doing partial reconfiguration so we could sort of download applications, or would it just be at image build time?
So for the kind of stuff that we're doing at UCSD, we're just going to be reloading the whole thing. So that's not really a bridge that I've crossed over yet, but that's definitely something that we could look into. I'm not sure if you have some specific requirements there, but it's like whenever you do partial reconfiguration, it brings in a whole bunch of logistical complications that you have to deal with, right? You got to make sure that the image you're loading has been built for the, outer part that's already running on the FPGA or whatever. So keeping track of all of that adds, an additional layer that makes things more complicated. But there's definitely advantages to doing stuff with, pluggable, reconfigurable sections. One thing I will say is that with the DMA infrastructure that Corundum uses, there could be some significant advantages to doing partial reconfiguration in terms of, since it uses this segmented interface that's possible inside whatever partial reconfiguration region that you have to kind of adapt that interface to whatever your logic requires. So, if you need AXI streaming interfaces, you can do that. If you need, an AXI master or an AXI slave, if you want, you can do that. And that's something that's, not really supported by things like the, like the Xilinx QDMA IP or the Alveo framework, right? They give you an AXI stream interface or an AXI interface kind of in the, at the edge of the reconfigurable section, and that you have to deal with that. But that's not a path that I've gone down very far. If that's something you're interested in, we can certainly talk about methods for potentially making that easier or supporting that particular use case, in Corundum architecturally.
Yeah, I think that might be useful. And that opens also another path of use of Corundum is as a compute accelerator, and probably maybe not even use the NIC part. Right, so some of like the queuing stuff might be useful to some applications, and you could use from over the PCIe just as a computer accelerator, not use the network parts at all. But I don't know if Corundum is like, that's a good direction for Corundum to go for.
It's funny you mentioned that. I was actually doing some thinking about that with RDMA support. It's like, some of those RDMA support components, like, the protection domains and whatnot, potentially you could use that separate from the network interface for communicating with an accelerator on the NIC. And you could use, say, the RDMA stack, for example, kind of as a DMA and communication engine to get stuff, onto the design locally and back off again without, necessarily sending any traffic over the link. And if you're not sending any traffic over the link, then, you could ignore those, or you could even run on boards that don't have any network interfaces if you wanted to. So that's definitely use case that's worth thinking about. I'm not sure exactly what that would look like at the moment in terms of if you're not registering any network interfaces, what would you have to do in the driver and whatnot for that to work? Not sure, but if there's enough interest in that and people want to work on that, then I would be happy to kind of facilitate that discussion and try to make that a reality.
Well, we looked into that subject a year ago for a client, which in the end didn't buy the project, but it was using large Xilinx FPGAs and to partially reconfigure them and the Xilinx tools do not allow to relocate IP blocks. So with our tools, it would have been able to load accelerators with a defined interface into one of those areas, which would be compatible to wire up to the to the top bus. It's possible, but yeah, in the end, the client didn't buy it because it probably was a little bit too far down the road. But we heavily looked into it, and if someone is willing to spend money on it, it can be done.
Yeah, I know there's quite a few researchers that are looking into doing some strange stuff with partial reconfiguration. So not my cup of tea at the moment, but I know there's definitely been a lot of work and a lot of research in that direction.
Yeah, well, the question is the official Xilinx tools are not capable pretty much, but the hardware is. So you could use the hardware which exists by just ignoring the Xilinx tools. And some researchers rewrite the bit streams to do this kind of partial reloading, but no one did yet. So one question about, because you said you will use a subset of system Verilog, mainly Verilog. Yosys is supporting standard 2008 Verilog. Is that something you consider to be Yosys compatible?
I think so. I have not really spent too much time looking into Yosys because it doesn't really support, the high-end parts, or at least I'm not aware of it supporting, the parts that are necessary to run Corundum. But I guess there are aspects outside of, just being able to synthesize code. So you're using Yosys not just for synthesis, but also for verification?
Yes.
Yeah, so I mean, right now, Corundum is written not even in system Verilog, but just in like Verilog 2001 or Verilog 2005 or something like that. I'm not exactly sure what specific version of Verilog I'm using, but and that's because we have some Vertex 6 boards that some of the libraries I've written have to run on. So like the Verilog Ethernet code, we have a couple of these gigantic high-tech global Spartan or Vertex 6 boards that we've used in the past for some research projects. So because we have to run stuff occasionally on those boards, some of the libraries that are used in Corundum have to run an ISE. So as a result, all the AXI stream stuff and the Ethernet stuff is all written in, normal Verilog that ISE will be happy with, at least for Vertex 6 devices. So I don't know about actually moving more of the design to system Verilog. It wouldn't necessarily be a problem, but because all the AXI stream libraries and AXI libraries are all written in Verilog without using system Verilog interfaces, I'm not sure how much benefit there would be at this point. But I'm not necessarily opposed to doing that. It's just, I don't necessarily want to rewrite all of my libraries and, maintain two versions of some of these things.
Yeah, well,
yeah, since
the open source formal tools support Verilog, plain Verilog. You can use that for free. So that would be one of the advantages if you would stay with Verilog.
Right. Yeah. Personally, I've not done too much with formal verification, but if somebody's looking for a project and wants to, work on formally verifying, pieces of Corundum, that's definitely something that that somebody could look into.
Hi, Alex. Ollie Bunting here, ETL Systems. We've spoken briefly over the internet before, so we've got an interest in running this NIC on a Zinc MP platform.
Right.
So the front end here, so it seems to be very coupled to the PCI Express in its current incarnation. Is that a valid observation?
Less than you might think.
Okay.
But so the way the DMA infrastructure is designed is that there's a a DMA interface module that bridges kind of the internal data path to the external interface. Right now, the only one in the repository is the PCI Express DMA interface module, but I have one that I have not tested in hardware yet, but I have written that's an AXI DMA interface module. So if you swap out the AXI one for the PCIe one, well, now you're running over AXI. And obviously you'll need to make a few tweaks to the driver. I've actually already gone down that path a little bit to try and segment out all of the PCI Express specific stuff into the top level probe methods so that we'll be able to add, basically a platform device driver top level, and then you'll be able to run it on a Zinc device or, something that doesn't have a PCI Express interface.
Yeah, so I've had a look through that.
Yeah.
The other thing I guess is interesting is, so currently there's some checksum and hash offloading.
Yeah.
So does it currently support full UDP offload? And
full UDP offload is in segmentation offloading, or
segmentation
offloading?
offload.
Okay, so right now Corundum doesn't support any segmentation offloading. It's dependent on the network stack to at least do software GSO, and that's actually not too bad because Corundum can do scatter gather DMA. So with software GSO, what you can do, or what the operating system does, is it doesn't actually copy the data around. It just creates, it just writes out all the headers for all the pieces of the transfer, and then slices up the buffer and points. It creates pointers into that buffer. So it's low overhead from the standpoint of the operating system. Doesn't have to copy everything, and tends to get pretty good performance. Once we turned on scatter gather DMA and Corundum, the performance would zoop because the operating system didn't have to copy everything. But hopefully, once we have variable length descriptors working, we'll actually be able to implement LSO in hardware. And as part of that, we're probably going to have to revisit the checksum computation. But we're going to have to revisit that anyway, because in RDMA, you're going to be generating the UDP packets on the FPGA. So with the current one, they're kind of tied to the networking stack that has to compute, the partial header checksum, and then the checksum offload just computes basically the payload checksum and then updates the checksum in the packet. But it should be possible, with the new ones to do everything self-contained.
Okay, thank you.
Sure.
And I'll just add my weight also from Edmund on the benefits of using the Yosis formal verification on your libraries. They come strongly recommended.
All right, I'll definitely take that into consideration at some point.
Well, at least there are the AXI properties already available. So, and from our experience, I can tell you all AXI implementations are buggy.
Yeah, it's a hard protocol to get right.
Yes,
I've definitely had my share of bugs in that. But so the thing with the Corundum is we were running into more performance issues with AXI. It's not really all that great of a protocol to interface with a DMA engine due to AXI can support all sorts of reordering, but sometimes when you have a DMA engine, you want to force a specific ordering, and it doesn't work so well with AXI and kind of the default way of building some of the interconnects. So now that we've moved away from using AXI in the core data path, that's less of an issue.
Yeah.
But now we're going to be bringing it back, so we could definitely trip over a few bugs. But the flip side is, since I have the open source library, if we find a bug, we can fix it instead of, yelling at Xilinx and hoping they do something about it. All right, so are there any other questions? I haven't heard anything from Alberto. I guess
I'm here. I do.
Yeah.
They're very specific. I want to spare everyone.
Oh,
So,
that's
okay,
fine. I mean, we're
you
already
poked the
over the
bear.
1 hour here, so everybody that has a time constraint is already gone. So
You poked the bear. So no, it's very little details, and I think I kind of I think I know what I'm expecting, but so the rookie versions, you know, some people operate on V1, some people operate on V2 just because of the good put. If you can't afford to operate on V1, you know, it's interesting. I certainly benefited before. Again, all my questions are going to be like this sort of decisions, and I guess your answer is, well, it depends on what's reachable and who needs it first or who's implementing. But, you know, things to consider. You know, your phase 2 seems a little more. Your phase 2 is not atomic. You know, it's not going to be in one increment. There's a lot of steps in there, and there's sort of a way of trying to line up what's next so that you get some subset of the functionality functioning very early, but then there's a long way to complete the functionality. And in that vein, and I think you stated it before, you want this thing to be interoperable, right? So if we're talking to a Connectix card, as long as, you know, the Corundum supports that particular subset of functionality, you might as well be talking to, you know, things are going to interoperate. The other thing is, like, you actually picked XRC, and I was wondering why XRC instead of DCT. This is a completely, you know, let's take it offline kind of discussion, but it's a very advanced.
So DCT is the dynamically connected thing, right?
I think they discontinue XRC. I'm not sure. I need to check. So I made a note of this one.
So yeah, the latest version of the IB specification has a whole section on XRC. So that definitely seems to be a thing. Basically, the reason I looked at XRC is, but there's a couple of reasons. The first one is the dynamically connected thing. It seems like you're going to have to do kind of a lot of connection state management somewhere. I'm not sure if that needs to be done in hardware or in software, and that's going to add some complexity. And then the other thing about dynamically connected is that because they're dynamically connecting the Q pairs, you can't rely on, you know, the Q pairs always talking to the same destination. And that's kind of important for, you know, the scheduling that we're trying to do in Corundum, where the Q pairs are, you know, going to be talking to a single destination. And we know what destination that is, so we can adjust the scheduler to, you know, do the right thing with that data. So with XRC, it seems like that you'd be able to kind of keep that setup where all the Q pairs are going to be talking to a single destination, but it gives you the ability to, you know, basically tunnel a bunch of connections over the same, you know, Q pair link.
I just want to make sure that XRC didn't accidentally end up in the standard, which would be weird. And I'm not even sure if
XRC is definitely in the standard, but if nobody implements it, then I guess it's a different story.
That's the question. So I just want to look into if Mellanox is behind DCT now, and XRC was just a step on it that ended up a step for it that ended up on the standard or not. That's the
okay.
Thing. And one more thing to mention.
Right. Well, sorry, I mean, let me put it to you this way. XRC is more interesting, you know, in terms of being able to integrate with the experiments that we want to do than the dynamically connected.
Got it. So you should totally, yeah.
Right.
So yeah.
So if we're going to implement one or the other, we're going to implement XRC.
Fair enough.
I mean, the other thing with XRC is it seems like it may not require all that much in terms of additional logic resources and functionality to implement. Right, versus something like dynamically connected. Although I guess on the flip side, dynamically connected, you maybe don't require any additional logic resources because they're just repointing the existing Q pairs. So I don't know, maybe there's a possibility there, but it's going to require some more thought. And I wasn't able to find all that much information with the quick searching that I was doing for the dynamically connected. So
I just want to make sure that people are using exactly. Is this thing catching or not, and what's the support level? Now, one last thing that I noted as well, and this one is super important if you're doing high speed at Roki, especially if you're doing Roki V2 UDP, you have packet loss. It's not if, you are going to have significant packet loss. If your application protocol supports it, great, but that's not always the case. And I have a good experience with, I have little, but very positive experience with doing lossless networks. With configuring the switches and the NICs. And this is one of the things that kind of really changed the outcome of my, well, the quality of my life and the outcome of my experiments is you don't have to worry about packet loss anymore. right?
Right.
Implementing PFC on the card would be kind of interesting. And
Right.
it
Yeah, I
boils
guess I
down
didn't
to-
mention PFC anywhere, but that's definitely something that we're going to have to look into.
You said that it would be easy to implement a congestion control. The infrastructure would be there at some
Yeah,
point.
I think so.
So this is, I think, of all these things, row key, XRC, DCT, those things are secondary. Lossless is a way to implement lossless networks is going to surface as soon as the thing is working and you crank the speed. That's the next thing that you're going to need.
Right. Well, we could potentially look into, that as part of, kind of the phase 1 functionalities, implementing pause frames and whatnot, because I think it's going to be pretty similar. So we could probably get that working before getting too far down, getting RDMA itself operational.
That'll be very nice. These are the things that I wrote down. And by the way, thank you for spearheading this effort. Much appreciated.
Yeah, well, thanks for connecting. Well, actually, one other thing is that you mentioned Rocky V1. So there's actually a decent number of people that are using Rocky V1, which is just over Ethernet directly.
Well, if you care about good put and you're not crossing subnets, it is a big deal.
Right, because you don't have all the UDP and IP headers.
Yeah, my packets are super small, so the good put, like, it really makes a difference. But then again, you're not going to cross subnets. Now I'm operating, you know what I'm doing. It's like it's basically experiments. I don't know if in the real world people are actually going to use V1. If you actually have situations where, yeah, you're kind of isolated anyway. So, because that's the difference. I think with V1 you cannot cross subnets.
Right, or you'd have to use, well, yeah, I guess because it's raw Ethernet, you can't do that. So, but I guess if you're building a cluster, that's probably not that big of a deal. That's just a design constraint you have to take into consideration. So
this is the thing. Like, it looks great because it really changes. Some of my goals have to do with the good put, but I don't know if if you get out of experiments, if this functionality is. I don't know if people are actually using Rocky V1 out there.
Right. Yeah, I mean, I guess that's one thing we can consider is, what the differences are between V1 and V2, and whether it's going to be, a huge leap to implement both, or, if it makes sense just to implement V2.
Well, V2, you need all the UDP. You said you had the UDP stack already, but you need the entire UDP stack on the card. Everything else should be the same.
Well, right. So V2, I mean, you need the UDP headers and whatnot. So you got to do some more checksum computation, perhaps, and filling in a couple more fields. I'm just trying to figure out, is that the only difference, or are there also some other differences? I mean, I think that's definitely the main difference.
Well, yeah, I can't think of anything big.
I guess
the package should be the same. Even the InfiniBand portion of the package should be the same. You're going to be doing all the switching and routing.
So I know one difference is that there's an additional InfiniBand header that's used in Rocky V1 that's not present in V2. I'm drawing a blank on which one it is, but it's basically it's superseded by the UDP header. So you don't need that InfiniBand header when you have the UDP header.
I haven't gotten to this level of detail. Yeah.
No, I have no idea how Rocky works on the software side, but I have been taking a look at the hardware side of the specification. So if people are interested in that, I have. You can download copies of the, well, I guess 1.4 version of the specification from the InfiniBand website. So I can send links around if people are interested in that.
I did. I got yelled at because I like to print the specs. So
it's a big one. Yeah. Yeah. The funny thing is, for the longest time, I was only able to find, I guess, volume 2 of version 1.4, which is the physical layer spec. It's like, okay, that's nice. I want the protocol layer version.
Yeah, you send me the trick. It was pretty.
And then I found it via URL fuzzing. You just change the ID and you get the the other volume. Yeah.
The last thing is also, like we started with Andre, that it's logged in here as well. We started looking into lib-ib verbs,
Right.
and starting to understand, because I mean, there must be a lot of indirections built in there, because we were toying, you know, we spoke about it with RDMA over NTB, and your application is still lib-ib verbs. So we want to understand what kind of level of indirection, probably a lot of indirections you have in there on how to send QP information to the card, and then how to post the operations to the card. And these are done probably in different ways. So we think some of the things are done via IO control, and some of the things are done via writing to memory. Anyway, like, we need to do a good read on lib-ib
Yeah,
verbs.
so
I think
I was actually just taking a look at that a couple of days ago, because I'm like, what, are we going to have to like fork lib-ib verbs and make our own version of it? But it seems like it's kind of, well, it seems like it's kind of split into a couple of pieces. So one of them is lib-ib verbs itself, and that's kind of like the public API that that your application will interface with. But then there's kind of a device-specific backend, and every device has their own backend library. So it's like lib-ib verbs doesn't directly talk to the card. It talks to this backend library, and then that talks to the card. Because otherwise, I'm like, well, how in the heck do you make this work with, you know, different implementations? Because every card is going to have their own, you know, descriptor, you know, format, and, you know, their own protocol for doing various things. So you have to abstract that out somehow. And I think that's how it works. Now, I'm not sure how some of the higher level stuff works. Like if you look at OpenMPI that uses UCX, I don't know if that uses, you know, lib-ib verbs and whatnot internally, or if they pulled in some more functionality into their code because they wanted to run faster on Mellanox NICs or something. So not sure about that. So definitely lots of things that need to be looked at, and, you know, varying priority levels.
That's kind of surprising if there's any other entry into the RDMA stack other than IB verbs. Yeah, not yeah. But we will continue on the next couple of weeks. Next few weeks, we need to accomplish something, and we're going to end up needing to understand lib-ib verbs a little bit better. But you're one step ahead of us.
Well, I don't know about that.
So that's
I'm looking at the hardware side. The software side is completely new. So I don't know if I mentioned this before, but you know, if you're interested in helping with Corundum and you're not an RDMA expert, well, you're in good company, because I have never used RDMA before. So I've just been reading over the specification.
It doesn't make it. The problem is the implementation history is it's a black box there. You can read the code, but there's not much. I couldn't find any documentation elsewhere. From the Mellanox side, the drivers, it's actually a tree of drivers with a lot of complexity in it. And I'm assuming it's complex because they use the same set of drivers, whether you're doing Roki or actual InfiniBand, whether you're using RDMA or IP, they use the same set of drivers. But they did publish the tree of drivers and how one calls the other. But other than the names, there's not much of exactly what they're doing. So there's some mechanics that we were looking in terms of, we think protection domains, not protection domains, but memory regions actually pin pages to memory. And we want to understand exactly how, and once those pages are pinned, who does address translation, you know, because you have to inform the cards of the page. So probably a driver does address translation and said, hey, this is the memory region, this is the page table area corresponding to the memory region. And we read somewhere that the page table is just copied to the card. It's pinned in the operating system and it's copied to the card. So anyway, lots of things to discover in there.
Well, I think the nice thing is a good portion of those drivers are open, unless
I think
I'm
they are
mistaken
all,
about that. I know all the kernel code that's upstreamed should be, you know, readable. I mean, well, for some definition of readable, right? you can go look at it in the kernel tree.
No, the code, I've seen bad code on the tree. The code's pretty good. The problem is they don't publish the design behind it. So you have to reconstruct the design piecemeal, and the design is not trivial. So, I think you get the best code possible to recover the design, but it's just, again, in one pass, you're not going to pick up the design right away. There's a bunch of things in there. And like I said, sometimes they're implementing a feature you're not really aware of. This feature may be, I don't know, it comes from the IP stack, or it comes from the InfiniBand stack, and you're not interested, and you can't figure out if that thing is relevant to you or not. So there could be some difficulty in that sense, reading the drivers. Yeah.
Well, I think we'll just have to take it, one step at a time.
Fair enough.
I mean, I learned how to build a NIC by looking at the Mellanox Ethernet drivers. So, there isn't exactly, no precedent for this sort of thing. But yeah, it's RDMA is definitely a more complicated beast.
Yeah, we should plan this. Like if more of us are reading the drivers together, then we could be able to tackle it easier. I don't know. We can coordinate if you think this is helpful.
Yeah, certainly. I mean, I would be open to having more of these kind of Corundum development meetings, if it helps, coordinate development efforts and get people talking. I know this is probably not a particularly great time for some of the folks at KAIST if they're interested in helping out. Maybe what we should do is alternate between a couple different times or something. But
they're 5 hours ahead. Yeah.
Yeah.
Yeah, kind of late in there.
So, I figure if we do more of these, maybe we can alternate between a couple different times or something. But yeah, we can definitely do more if this is useful for people. All right, well, it looks like people are starting to drop out here. I don't know if anybody else has any questions or anything, then we can certainly discuss stuff. But this has been a good discussion, Alberto. So definitely we've got
sure,
a lot of work to do.
If you want to make people disconnect, just bring me in the discussion.
And there's probably people that find some of this stuff interesting.
No,
but
I
yeah,
know. People have other times, but I think the attendance was great. I mean, I saw 31 people when sustained. It's not that people were logging in and checking. It's like people stayed the entire hour. So a very, very diverse group. So yeah, and I like the survey as well. So the survey is kind of, hey, are you gonna chip in? Where?
Yeah.
Sort of, where are you? What areas are you interested? So I'll be curious to hear the once you have a chance to compile this thing, if the group is heterogeneous and you got all the areas covered, or if everybody's focused on the same things.
Right. Yeah. Well, just looking at what people posted in the chat, it looks like we got people from Xilinx Research. We got somebody from Intel Labs. We got
Sergio,
a bunch of different institutions. So yeah, that's pretty good group of people. I guess we'll see how things play out going forward, but this has been a pretty good start, I think.
I agree.
I was hoping to see a few more people from UCSD, but I guess.
I mean, it's people from the house. They never was like, oh, I can ping Alex whenever I want. So they probably,
true. That's
they have access. Alex, so I'm in the middle of a conference here. I'm going to check out as well. I want to thank you again for putting this effort together. I saw that people were thankful as well. So a few notes on the message. Just want to make sure that you get some recognition. We all appreciate this effort very, very much.
All right. Well, thank you very much. All right. See ya.
I'll talk to you soon. Thank you.
Sounds good. All right. Thanks for dropping by.